Welcome all to this session, which is going to give you a brief introduction about dynamics and engineering mechanics, and then it will discuss the rectilinear kinematics and continuous motion. The objective of this session is to define engineering mechanics and dynamics, as I explained, and then we will talk about the rectilinear kinematics, in which we are going to discuss position and displacement, speed and velocity, and then we will talk about acceleration. Now, engineering mechanics has two branches. The first one is statics, and the second one is dynamics. In statics, we deal with the equilibrium of body. Summation of forces equals to zero. Summation of moment equals to zero. And this is exactly what you covered in Statics, Civil Engineering 201 course. In Dynamics, we are going to deal with kinematics and kinetics, which I'm going to explain the differences. And on the two, we are going to basically consider particles, rigid bodies. We will then also talk about forces and acceleration, work and energy principle, impulse and momentum. All will be discussed in details all over the course. Now, so to give you a brief kind of comparison between statics and dynamics, in statics, we deal with equilibrium, as I said before, and this means that we discuss or we consider bodies that are either at rest or at a constant velocity. While in dynamics, we deal with accelerated motion of the body. And in dynamics, we have two branches, as I said. One of them is the kinetics, and the other one the kinematics, and the other one is the kinetics. In kinematics, we treat only the geometric aspect of the motion. This is going to be clear as we move on. While in kinetics, we analyze the forces that causes the motion. Now, if you look at this example, if, for example, you look here, if this were to be a statics problem, then you will be asked to determine the forces acting at a certain point, like, for example, joint D or C. So you will be asked to find the reaction, the forces acting on that point. While in dynamics, you will be given, for example, some acceleration, or like here we have an angular velocity of 0.3 radian per second at a certain axis, and then you will be asked to determine the velocity or acceleration or even the position for a particular point, like, for example, point C or B or any other part of the body. So this is basically the difference between the two. Now, let's now start talking about the rectilinear kinematics and continuous motion. And I just want to tell you that the key words here are rectilinear and kinematics. So, as we discussed earlier, the kinematics means that we are going to deal with the geometric aspect of the motion. For the rectilinear motion, we are going to define the word rectilinear for you in a minute. So, to start with this, we need to have a clear definition about the rectilinear path. So, rectilinear path is a straight line path. Straight line means straight line, just one line, no curvature. And what is really important here is the assumptions that follows. So, the assumptions here, assumption number one, is that the dimensions of an object have no consequences in the analysis of the motion, which means we don't care if we are studying a rocket or a ball. It doesn't matter. Both are the same. The objects are treated as particles, and the word particle is a key word because particles has mass but negligible shape and size. So This is why we treat rocket as a small particle. Motion is characterized by the motion of the object mass center, and the rotation of the body is neglected. So the rotation here is basically the spin. So even that particle, we don't assume that that particle will spin. These assumptions are very important, and I'm going to try to remind you about them as we move on. Now, so to characterize the rectilinear motion, we need basically to define the position, the displacement, the velocity, and acceleration. And by the way, this is what we are going to do again and again and again. Now, to start with the position and the position vector. So the position of a particle is represented by an algebraic scalar S over here. And what is that? Basically, we have an axis over here in this diagram. Okay? And we call the x-axis here S, which represents the position. And the origin is right here at point O. Now, we can say that the position of this particle is defined by this S, which is the measure of the distance from O to the location of the particle. That's it. Now, the position vector R has a magnitude S, but it also has a direction. So if you look down here we have exactly the same diagram, but what we did, we pointed a vector going from here all the way to here. And that vector has a magnitude of S, but its direction is pointing, its arrowhead is pointing toward the particle position P. So this is called the position vector. And as you see later, we are going to use position vector to determine the displacement and then the velocity and then the acceleration. Now, position and position vector has unit of length, so either meter, feet, inch, or any other measure of. The displacement of a particle is a vector, which is called delta R, defined as the change in the particle's position vector R. So if you look here, the position of the particle was P, and then it changed to P prime. So its position at P was S, and then at P prime it became S prime. So the change in the position is delta S. Similarly, the position vector at P is R, and then the position vector at P prime is R prime, and the change in the position vector is delta R. Now, of course, the position vector delta R is a vector, and it will have a direction. So, for example, we can say that the right-hand side is positive, while the left-hand side is negative. Of course, I want you to take note here that I will write vector with the letter and an arrow on the top, while it is in the textbook as well as in the diagrams written as a bold letter. Now, the speed and velocity. The velocity is a measure of the rate of change in the position of a particle. And the word rate means that it changes with time. And if you look carefully in this diagram, you would see that the position of the particle at a given time was P, and then it changed to P prime. Now, so the amount of displacement is delta S. But if we have a stopwatch and measure the time for the particle to move from P to P prime, then, and we take the rate of that, what we are going to get is the velocity. Now, the velocity here is represented by this arrow, which is a vector, pointing to the direction of the displacement. Now, so velocity is a vector. Its magnitude is known as the speed. Its unit is length per time, so it's a meter per second, feet per second, or any other unit of length divided by unit of time. Now, the average velocity is defined as the displacement divided by the time. So we write it like this: average is equals to delta R divided by delta T. Now, if we know that this is an average measure. So if we want the instantaneous velocity, it is the limit when delta T goes to 0 for delta R over delta T, which is equals to dr over dt. So this is known as the instantaneous velocity. Now, if we want to know the speed is basically the magnitude of the velocity. So it is defined as the velocity, which is written like this, and it is equals to the magnitude of ds over dt. Now there is an average speed, and I am going to make a clear comparison here between the average speed and the average velocity. The average speed is the total distance traveled divided by the total time. So in this example, if you look here on the right hand side, in this example, the particle started from this position and then it moved to this position. So the trajectory of the particle was starting from here, going all the way backward to here. So if you want to define the average speed, then in this we write it like average, and it is basically st divided by delta t. What is st? St is the total distance traveled, all of this red path divided by the amount of time. Now, if we want to know the average velocity, then it is basically, as we said, the displacement over time. So it's going to be minus delta S divided by delta T. And delta S is defined as here. It's just the amount of displacement. It's not the total traveled path or distance. Now, we move now to the acceleration. Now, for acceleration is the rate of change in the velocity of a particle. And so it is similar to the same concept of the rate of change of the position is the velocity, and the rate of change of the velocity is the acceleration. Now, for that, if you look here, again, if the particle is at this position P, and then it moved to position B prime, and if we were to measure the velocity, then at point or at position P, the velocity has a direction, which is the right hand side, and a magnitude represented by the length of this arrow. But at point P prime, the direction is still the same, but the length of the arrow got longer, which means the velocity is increasing. And for that reason, the rate of change in this velocity is represented by the acceleration, which is again a vector represented by an arrow pointing toward the direction where the velocity is increasing. Now, this is what we called acceleration. Now, deceleration is different. In deceleration, what we have, the particle again was initially at this position P, and then it moved to position P prime. And however, By the time the particle moved from v to v prime, its velocity started to decrease. So representing this by the arrow, if you look at this arrow, it is longer than this. So the particle is still moving to the right-hand side, but its velocity is decreasing with time. And for that, we are going to have the acceleration pointing backward, opposite to the direction of the motion. That's a very important observation. And not only this, we are also going to have a negative sign on the acceleration. And this is what is commonly known as the deceleration. So for acceleration has a unit of length divided by time square. So it's meter per second square, feet per second square, and so on. Now, if we want again to define the average acceleration, then A average is defined as the difference in the velocity dv divided by dt. While if we want to know what is the instantaneous acceleration, then basically it is the limit when time goes to 0, delta t goes to 0, for dv over dt, which is going to give us dv over dt. Now we are going to construct the relation between the position s, the velocity v, and the acceleration a independent of time. And to do that, we are going to start by writing the velocity equation as ds over dt, or dt, which is equal to ds over v. Similarly, we can say that the acceleration is equals to dv over dt, or dt, which is equals to dv over a. Now clearly these two relations represent time, so we can say that they are equal. So ds over v is equals to dv over a. And now if we do a cross multiplication, then we are going to get a ds, which is equals to v dv. Now if we express this equation in a vector notation, we would have to specify the direction. For example, the right hand side positive and the left hand side is negative. This relation is very important and useful, as we are going to see later in the course. Now let's have this quick example. In this example, we have a car moves in a straight line such that for a short time its velocity is defined by an equation v equals to 3t squared plus 2t feet per second, where t is in second, and we want to determine its position and acceleration when time equals to 3 seconds, given that the position s0 when the time is equals to 0. Now to start with the position, so we will start with the position. For the position, we know that the equation of the velocity was given. So v, which is equals to ds over dt, was given to us as 3t squared plus 2t. Now we can also write this as ds, which is equals to 3t squared plus 2t multiplied by dt. And then we can integrate from 0 to s, and for here we integrate from 0 to t. And for that, what we are going to get, we are going to get s from 0 to s is equals to t cubed plus t squared from 0 to time t. So if we do the substitution, we will get s equals to t cubed plus t squared. Now, if we go and substitute at time, so at time equals to 3 seconds, we will get s equals to 3 cubed plus 3 squared, which is equals to 36 feet. And this is it for the position. Now we move to the acceleration. For the acceleration, we can use the same principle over here. A is equal to dv over dt, which is equals to d over dt of 3t squared plus 2t. Now, if we do the derivative, we will get the acceleration as 6t plus 2, which means that the acceleration is not constant. It's a function of time. Now, when t is equals to 3 seconds, we will get the acceleration equals to 6 multiplied by 3 plus 2, which is equal to 20 feet per second squared. And that's the end of the question. Now, to summarize, we discussed or we defined what a particle is. We also talked about the definition of kinematics and kinetics. We also defined the rectilinear kinematics by defining the position and displacement, speed and velocity, as well as the acceleration, and we ended with a simple example. That's it. Thanks a lot.